In this screencast, we want to nail down some theorems about dissection theory. And the first one is really, oh, we'll go black here. Really straightforward. Every triangle is scissors congruent to a Sakari quadrilateral, or a Khayyam quadrilateral. In Euclidean geometry, this automatically means that every triangle is scissors congruent to a rectangle. And here's the way that we do this. We take some triangle ABC, we find the midpoint of AC, and we find the midpoint of BC, and then we draw the line through M and N. We draw that line. The Sakari quadrilateral is formed by dropping perpendiculars to line MN from B and A. We call ABDE the associated Sakari quad for triangle ABC. It is worth asking how we know it is a Sakari quad. That's worth asking. In the case where in Euclidean geometry an ABDE is a rectangle, that's pretty straightforward. Parallel lines are everywhere equidistant. Here it's a little bit trickier. In the neutral case, you could drop a perpendicular to line MN from C also. It's pretty straightforward that triangle AME is congruent to triangle CMF. And it is also pretty straightforward that triangle CNF is congruent to triangle BND, which means that AE is congruent to CF and CF is congruent to DB. And there you've got an associated Sakari quad. That should be straightforward. So what does this mean? Just driving this home. Triangle ABC has the same area as Sakari quad ABDE, which means that triangle ABC can be cut into pieces and rearranged to make quadrilateral ABDE. I will also note that triangle ABC and triangle ABDE have the same defect, because in a neutral situation they have the same defect because they are made from congruent pieces, and all of those pieces have the same corresponding congruent pieces have the same defect, and defect is additive. Let me give you a Euclidean theorem here. Every rectangle is scissors congruent to a square of some kind. This is fairly straightforward. It's fairly straightforward. The proof by picture here actually generalizes nicely. So let's pretend that you have some rectangle, right? You got some rectangle, whatever. And you know that it's scissors congruent to a square of some kind. Maybe this is the square with the same area. But it doesn't matter because it generalizes nicely to any two rectangles of the same area. You can draw that line in, and you and I are both pretty sure that this little piece ends up down here, and this triangle basically slides down the purple line and makes the blue rectangle out of the red one. So in Euclidean geometry, every rectangle is scissors congruent to a square, and we can make it happen in this sort of a way. In the discussion, you're going to be expected to show that this little piece is congruent to this little piece, and that this triangle really does slide down and become that rectangle. So you're going to be expected to show that congruence. I'm going to assert that it's true and let you figure it out later. I should also note, still in Euclidean geometry, that the union of two non-overlapping squares is scissors congruence to a square. And I'm going to let you think about why the Pythagorean theorem is that result. So what's the deal? What really happens here? Every triangle can be turned into basically a rectangle in the Euclidean plane. Every rectangle becomes a square. Two squares together is a square. So triangles can become squares. I will also throw in this side note. Every triangle has what's called an associated parallelogram. And this is true neutrally. Same setup, same midpoints. Begging your pardon, this is a Euclidean result. Here's M, here's N. We draw this segment, and then we extend an equal distance. Then ABGM is a parallelogram. It's the associated parallelogram. And since it's the associated parallelogram, we know that triangle ABC is scissors congruence to parallelogram ABGM. Those are all things to be aware of. They help us know how to chop things up and put them back together. Hope this is helpful to you. Next up, area in hyperbolic geometry.